Hi, everyone. Welcome to our final project presentation.
So first of all, I'm going to introduce myself. I'm Tony.
I'm Jacqueline.
I'm Mario.
Hi, and I'm Shuang.
And I'm Gabby. So in terms of the table of contents, we will start with a description of our project, then we will delve into the process, and then we have a summary of our findings.
So our goal in this project was to predict the COVID-19 infection rate in different zip codes in Chicago. And so we wanted customers to be able to look at how infection rates might be in the future.
Since our data is for the city of Chicago, we decided our target audience should be real estate agencies that deal with property in the city of Chicago.
In terms of our data, its current size is 8,160 rows with 19 unique attributes that are listed below. Our target variable was cases weekly, which described the number of cases in 1 week in a specific zip code. And our data is from data.gov, which contains data from November 10th, 2020 to October 14th, 2022.
After we imported our data, we have studied it and we found these following on the top left, and then we cleaned by the methods on the bottom left. We also encountered some problems, such as the data frame was unsorted, so we have sorted it with zip code being priority, and then week number, and then the starting date. We also decided on our target variable after studying it, and then we removed the zip code 60666 because it's an airport, not residential. We were also not able to use an ROC curve because we are not doing classification. We created a time series because we realized that this COVID infection is seasonal. We converted a week start date into a bar format date so we can extract its year and months to use in time series.
So also we're building other models. We're doing the 10-fold cross-validation and then put the result together to get a better performance. We're using logistic regression, naive Bayes, decision trees, and k-nearest neighbor. First of all, we have logistic regression. We use 10-fold cross-validation and split the data into training and testing sets. We built the models with GLM package, and we predict the cases weekly using this model.
As we did with logistic regression, we also used 10-fold cross-validation and split into training and testing sets. This time we used the E1701 package to build our model, and we predicted cases weekly again.
We also used a decision tree, again, using 10-fold cross-validation, and we used the R-part package to predict cases weekly.
Following along those lines, for k-nearest neighbor, we used a 10-fold cross-validation and built the model using the KKNN package with the feature zip.code as numeric, distance as 1, and the number of folds or k as 9. We then predicted cases weekly using that model.
While building the model, we encountered some problems, such as a warning from the logistic regression model, which can be ignored. While we used time series, we had to sort the data, so we sampled randomly again in order to create equal folds.
So then to test the accuracy, we found the mean percent error, the mean squared error, as well as the accuracy, recall, and precision of all of the models. And then we found the accuracy of the average of the accuracy measures and stored for comparison later, and repeated this process for all of the 4 types of models. And that process is shown on the right, how we did that in R. So then to compare, we created a table with each of the different accuracy measures for the different types of models, allowing us to compare them. And it was found that naive Bayes has the lowest mean absolute percent error, and so is the model that should be used. And it's important to note that the exact values for the accuracy measures will be slightly different every time the program is run because the folds are created randomly. And so the models will be different each time. Then we graphed the predicted values against the actual values for each of the different models. So this is the graph for logistic regression. And so you can see that the predicted values were very likely to be lower than the actual values. This one. And then here are the results for the naive Bayes model. And again, we see that the predicted numbers were lower than the actual values. And you can also see that the lower the actual value is, the more accurate the predictions seem to be.
This is the result from graphing predicted versus actuals in the decision tree model. Even though the scatter plot looks weird, if we were to draw a line of best fit, it will run along the diagonal pretty accurately.
This is our comparison between the actual and predicted values for the k-nearest neighbor model. And as seen before, the predicted numbers were more likely to be lower than the actual numbers.
To further visualize the data, we created several graphs and maps. On the left, we have an animated bar graph with zip codes on the y-axis and the number of cases over this time period on the x-axis. On the right is the same data, but it's represented as a heat map, and the darker colors are higher case totals. And we also decided to see how different seasons affect the case totals, because certain seasons might carry certain sicknesses. On the left, we have the number of cases by each season. And on the right, we have the number of cases by each season and year. So as you can see on the left, winter has just about 300,000 cases. And on the right, we could see most of those cases come from the winter in 2021.
So that'll be it for all our presentation. Thank you for watching.